All right, well that didn't work. Let's go back to first principles. Is there a theorem I can use here? Well, it's not obviously a Cauchy-Schwarz inequality. Just getting rid of this stuff here. It doesn't hurt to try stuff out. Doesn't hurt anybody. ABC equals 1, a cubed over this plus b cubed over that plus c cubed over that. What I'm going to do is I'm going to assume you write W log without loss of generality that A is greater than or equal to B greater than or equal to C. So I've just put they're all strictly positive anyway, but I'm just going to assume that they're in that order. Now if this is the case, what about 1 over 1 plus B 1 plus C compared with 1 over A, 1 plus A, the next one, 1 plus C. Well, you can see quite easily that because what's changed? There's one of the C is common, one of the B is common, but we know that B is larger. Okay, so what that tells us is we're dividing by the larger thing here, and so this is going to be smaller than this. So 1 over 1 plus B 1 plus C is greater than or equal to 1 over 1 plus A 1 plus C, and that in turn is greater than or equal to the third denominator, which is 1 over 1 plus A plus, oh dear, I don't quite understand what that is. Oh, I know. Yeah. 1 over 1 plus what's the last one? 1 over A 1 plus B. This guy's the smallest one because you're dividing by the two biggest numbers, because A, B and C. So you see we've picked apart this expression here into two bits. A numerator which is in order, because A is greater than B greater than C, that tells you that A cubed bigger than B cubed bigger than C cubed, because cubed is a monotonic function. But now we've also, by virtue of ordering these guys, we've also put the denominators in order too. So let's try using that. Can we remember what the rearrangement inequality is? The rearrangement. We might need something more powerful, but let's just have a look at it. Rearrangement inequality. The rearrangement inequality, which was screencast number 14, I think I talked about it. Let me just state it again, and then what we'll do is we'll fool around with it and see if it helps us at all. So we've got A1 less than or equal to A2 less than or equal to blah 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 less than or equal to AN. B1 less than or equal to B2 less than or equal to less than or equal to BN. And that tells me that A1 B1 plus A2 B2 plus A3 B3, you may as well stop at 3, is greater than or equal to A1 dash B1 plus A2 dash B2 plus A3 dash B3, where A1 dash A2 dash A3 dash is a rearrangement of A1, A2, A3. Okay, it's quite a powerful theorem, that. Now, I'll just check that we're going the right direction. We need to show that this guy here is greater than or equal to 3/4, but multiplied by the terms in some other. I can shuffle those denominators about, perhaps to my advantage. Let's have a think about that. Which one could I use? 1 over A cubed. How could I do that? Just a minute. Well, we can just rewrite it. A cubed over. We've got the rearrangement equality, so I can say that the left-hand side, which is going to be this guy here, is greater than or equal to A cubed over, well, what can I do? What denominators have I got to play around with? Well, I've got 1 plus B there, 1 plus C, 1 plus A, 1 plus C. I can choose. We got this one originally, plus the other terms there. But I can have A cubed over 1 plus A, 1 plus C, plus let's try B cubed over 1 plus B, times another factor which I'll choose in a minute, plus c cubed over 1 plus c. So I'm just rearranging it. It can't be 1 plus a, that must be 1 plus b here, and that must be 1 plus a. Okay, so the left hand side is greater than or equal to this. Has that done us any good, given that ABC equals 1? Has that done us any good? No, I don't think it has. Because you'll remember in the last one, I used the AM-GM inequality, the arithmetic mean geometric mean inequality, and that was a fat lot of good. That just didn't work. And because all I've done is rearrange the denominators, that hasn't helped. I thought that because we've got an A in the top and an A in the bottom, that I might be able to cancel it somehow or do something clever with it. But I don't think that's happened. So this is a big fat fail as well. But I can't help thinking that this observation here, that the numerators are ordered a cubed, b cubed, c cubed, implies that the denominators are in the same order. That means that the rearrangement inequality is going to kick in here somehow. I don't know how, but it's going to kick in. So what we're going to do is keep hammering away, and we'll use a more powerful version of the rearrangement theorem. We'll use Chebyshev's inequality. The next screencast. Stop there. Stop. Done.